Its target cuts left. The cheetah is already too fast to follow, so it does something that sounds completely wrong. It slams on the brakes. Its paws bite, its body leans, and its tail swings across. The fastest land animal survives the corner by deliberately giving up speed. That is the secret most speed records miss. A cheetah's hunt is not won at maximum velocity. It is won by controlling velocity. Researchers fitted 5 wild cheetahs with collars that track their motion. Across 367 recorded runs, the fastest measured burst reached 25.9 meters per second, about 58 miles per hour. But that number was the exception, not the normal chase. Most hunts happened at moderate speeds, with rapid acceleration, hard braking, and sharp changes of direction. So why build an animal capable of extraordinary speed if it rarely stays there? Because speed is only one setting. The real superpower is shifting between settings almost instantly. To see how that works, freeze one high-speed stride. A cheetah uses a rotary gallop. Its feet strike in sequence, not as neat left-right pairs. Then all 4 feet leave the ground while the legs fold beneath the body. This is the gathered flight, and the cheetah seems to compress around its curved spine. The spine extends, the front legs reach ahead, and the hind legs sweep backward. For a second time, every paw is airborne, but now the body is stretched long. 2 flights in one stride, gathered, then extended. Between them, carefully timed footfalls redirect the body and prepare the next launch before the previous one looks finished. Racing greyhounds also use a double suspension gallop, but treadmill measurements found a revealing difference. As cheetahs ran faster, they increased stride frequency as well as stride length. The famous flexible spine helps create those extreme body shapes. When it flexes, the hind limbs can swing farther forward beneath the torso. When it extends, the reach opens again. A computer model of cheetah galloping supports the idea that this flexion and extension contributes to high-speed motion by coordinating the trunk with the legs. But supports matters. The model does not prove that the spine is a giant spring powering the animal by itself, or that one simple mechanism explains every stride. Muscles still move the limbs and trunk. Tendons, joints, ground forces, foot timing, and the animal's posture all interact. The spine is one moving part in a linked system. Its flexibility expands the range of positions that system can use. The cheetah can lengthen a stride, gather its limbs for recovery, and prepare a new footfall at remarkable speed. Running speed comes from 2 levers: how far the body travels with each stride and how many strides happen each second. A cheetah can pull both. That helps explain why its gallop is not a fixed loop played faster. Its stride changes with speed, almost like shifting gears, while every limb is already in motion. On a straight burst, longer, quicker strides build velocity. Near prey, the job changes. The feet must land where they can push, brake, or redirect the body next. The same field collars that captured exceptional speed also recorded exceptional acceleration and deceleration. And that second ability is where this chase stops looking like a simple race. Turning becomes brutally expensive as speed rises. For the same corner, doubling speed requires roughly 4 times the sideways force. No flexible spine can cancel that physics. A fleeing animal can exploit the problem by changing direction. If the cheetah charges through at maximum speed, its wide turning path may carry it past the target. Braking shrinks that path. It also gives the cheetah time to reposition its feet, change its lean, and choose a new line before accelerating again. Broader predator and prey research found that predators have advantages in muscle power, acceleration, and deceleration, while a smaller prey animal can still gain a maneuvering advantage in a turn. That makes the chase a moving compromise. Every burst closes distance, but every extra bit of speed makes the next surprise harder to answer. Control is not separate from speed. It decides when speed is useful. Then there is the tail. People call it a rudder, as if it steers the cheetah through the air. The real picture is more careful. Swinging a heavy tail one way can help rotate or stabilize the rest of the body the other way. That inertial effect can support fast adjustments during a turn. Modeling also suggests aerodynamic drag on the tail could add corrective torque. But that is modeled evidence, not a measurement proving the tail acts like a magic steering paddle in every chase. The cheetah turns with the whole animal. Paws pressing into the ground, limbs changing force, trunk bending, body leaning, and tail moving as part of the same coordinated correction. Now replay that opening cut. The prey changes direction, so the cheetah sheds speed before its momentum can drag it into a larger arc. Its feet find a new line. The body leans. The tail swings to help manage rotation, while the flexible trunk and rapidly cycling limbs organize the next stride. Then it accelerates again, not necessarily toward a speed record, but toward the right place. What matters is matching each burst to the prey's next move. A real hunt is a chain of launches, breaks, and turns. Top speed is a brief tool inside that chain. The cheetah's deeper advantage is how quickly it can exchange speed for control, then take speed back. The headline is still true. The cheetah is the fastest land animal. But the hunt belongs to something more interesting, the body that knows when not to be fastest. And if you want another superpower hiding behind a familiar headline, watch how bats hear the shape of a moth. It is on screen now.